In this tutorial on industrial instrumentation, we will talk about flow measurement part 7. The topic of discussion are Vortex Flow Meter, under which there are three types: Swirl Vortex Flow Meter, Vortex Shedding Flow Meter and Fluidic Flow Meter. The Vortex Flow Meter is a flowing meter for measuring fluidic flow rates in an enclosed conduit. When the medium flows through the bluff body at a certain speed, an alternately arranged vortex belt is generated behind the sides of the bluff body, which is called one common vortex, repeating pattern of swirling vortices. Differential pressure changes occur as the vortices are formed and shed. This pressure variation is used to actuate the sealed sensor at a frequency which is proportional to the vortex shedding. For continuous flow, a series of vortices generates electrical pulses with a frequency which is proportional to the flow velocity. The velocity can then be converted to volumetric flow rate. The output of a vortex flow meter depends on the K factor. The K factor relates to the frequency of generated vortices of the fluid velocity, which is given as fluid velocity equal to vortex frequency by K factor. There are three types of vortex flow meter, which are swirl meter, vortex shedding flow meter and fluidic flow meter. In context of a vortex flow meter, the Kármán vortex state is a very important aspect. The Kármán vortex state, also known as von Kármán vortex state, is a repeating pattern of swirling vortices that is caused by a process known as vortex shedding, which is responsible for the unsteady separation of flow of a fluid around blunt bodies as shown in the figure below. From previous slide, we know that the fluid velocity is given by the formula velocity fluid equal to vortex frequency by K factor. The K factor varies with Reynolds number, however it is virtually constant over a broad range of flows. Vortex flow meters provide very linear flow rates when operated within the flat range. The fluid parameter which governs the operation of the vortex shedding flow meter is a non-dimensional number called Straw-Hall number, represented by S and expressed as S equal to Fsd by V. Fs is the vortex shedding frequency and d is the diameter of the bluff body, with V being the average velocity of the flow. The flow rate in a vortex flow meter Q is given as Q equal to pi by 4 d square Vu, or equal to pi by 4 d square minus hd into Vd, where Vu is the upstream flow velocity, Vd is the downstream flow velocity, h is the pipe diameter and small d is the bob diameter. The vortex flow meter comes in three different types: swirl meter, vortex shedding flow meter and fluidic flow meter. There are mainly 5 different types of bluff body, which are round, rectangular, two-port rectangular, T-bar and delta shaped. The first type of vortex flow meter is the swirl meter. The swirl meter combines the advantages of a turbine and vortex flow meter technologies. They have a very high turndown ratio and very high accuracy. They are reliable, robust and maintenance free. The vortex swirl flow meter operates on the principle of vortex precision. It gives an output in the form of pulses whose frequency is proportional to the fluid flow rate. It consists of a fixed set of swirl blades, usually made up of stainless steel, which introduces a spinning or swirling motion to the fluid at the inlet. At the downstream of the swirl blades, venturi-like contraction and expansion is provided with a temperature sensor. At the exit, there are de-swirl blades employed to straighten out the flow, leaving the meter. As fluid passes through the fixed set of swirl blades at the inlet, a swirling motion is imparted to it. A turbine-shaped inlet section forces the axial flow entering the flow meter into a rotational movement. A vortex core forms in the center of the primary rotation. A secondary rotation forms in the vortex core, producing thread-like spirals. The frequency of the secondary rotation is linearly proportional to the flow rate over a wide Reynolds number range. Pressure variations resulting from the secondary rotation are detected by a piezoelectric sensor and converted into an electrical pulse. In the area where expansion occurs, The swirling flow precedes or oscillates at a frequency proportional to the fluid flow rate. This precision causes variations in temperature sensed by thermistors. The amount of heat extracted is a function of the fluid velocity. The second type of vortex flow meter is known as the vortex shedding flow meter, where a vortex is shed from one side of the block body and the fluid velocity on that side increases with the decrease in pressure, and at the same time the velocity on the opposite side decreases with an increase in pressure, thus causing a net pressure change across the block body. The object introduced in path of flow is known as the block body. When the fluid flows past the obstacle, boundary layers of slow-moving fluid are formed along the outer surfaces of the obstacle, and the flow is unable to follow the contours of the obstacle on the downstream side. Thus, the flow layers are separated from the surface of the object, and a low pressure area is formed behind the object, which causes the separated layers to get detached from the main stream of the fluid and roll themselves into eddies or vortices in the low pressure area. Each eddy or vortex first grows and gets detached or shed away from alternate sides of the object. The frequency at which the vortices are formed is directly proportional to the fluid velocity. As a vortex is shed from the one side of the block body to the other, the fluid velocity on that side increases and the pressure decreases, and vice versa. The change in pressure or velocity is sensed by a flow sensitive detector, which can be either a thermistor or a spherically shaped magnetic shuttle. The third type of vortex flow meter is the fluidic flow meter. The fluidic flow meter operates on the principle of Quanta effect. The Quanta effect is a tendency of a fluid jet to stay attached to a convex surface. The tendency of a jet of liquid emerging from an orifice to follow an adjacent flat or curved surface and to entrain fluid from the surrounding so that a region of lower pressure is developed is known as Quanta effect. The fluidic flow meter consists of a turbulent jet which can be deflected from its central position due to the internal geometry of the meter body, and it is essentially attached to one of the side walls of the meter. As the fluid enters the meter, it is entertained into the jet from its surrounding, which causes a reduction in pressure. The jet curvature is sustained by the pressure differential across the jet. If sufficient volume of fluid is introduced into the control panel, it causes the jet to switch from the initial position to the opposite side wall. The jet can be made to oscillate in two ways. In the first method, two ports are connected together and the fluid is sucked from the high pressure side to the low pressure side, causing the jet to switch to the other wall. The jet thus continues to oscillate as the fluid is sucked alternately from one side to the other. The second method is the feedback oscillator system, in which the deflected jet causes low pressure area at the central port. At the upstream feedback passage, the pressure is higher due to a combination of the jet expanding and stagnation pressure. Thus, a small portion of the main stream of fluid is diverted through the feedback passage to the control port. The feedback flow intersects the main flow and diverts it to the opposite side wall. The whole feedback operation is then repeated, which results in a continuous self-induced oscillation of the flow between the side walls of the flow meter. The frequency of oscillation is proportional to the volumetric flow rate. The frequency is detected by means of temperature sensors like thermistors and other different type of sensors. Like the variable head flow meters, vortex flow meters also has two parts. The primary part, which is the block body, and the secondary part, which is used to pick up the vortices that are created in the flow path. The secondary sensing elements are thermal sensors, pressure sensors, magnetic pickup coils, strain gauge sensors, piezoelectric crystals, capacitive and ultrasonic sensors. The advantages of a vortex flow meter are: they are applicable for liquids, gases and steam. They have negligible wear and tear. They are low in cost and maintenance, and they are very easy to install. They are less sensitive to process disturbances, and therefore they offer good accuracy, stability, repeatability, and can cater to wide range of pipe sizes. They have wide range of temperature application. The few limitations are, however, they are unsuited for very low flow rates and for large unrecoverable pressure drop. A minimum straight pipe length is required for both upstream and downstream of the vortex meter. They can only measure unidirectional flow, and they are applicable only for clean non-conductive fluids and not suited for viscous fluids. Vortex Flow Meter finds application in dealing with custody transfer of natural gas metering, in steam measurement, in fluid flow measurement where there are suspensions, in general water applications, and largely in liquid chemicals and pharmaceutical industry. For more details and further reading, the students can refer to the following links and references. Thank you.